Hello students, welcome. Here in this short presentation, we demonstrate Lenz's law in our physics laboratory at Bennett University. Imagine a circular loop of a conductor placed in a magnetic field. This magnetic field, for example, could be produced by a bar magnet which is kept close to it. So there will be some field lines which go through the coil. So these are the field lines, and there is some flux associated with it. Now, if this flux changes with time, so for example, you could move the magnet closer or away from the loop, the flux will change. The Faraday's law of induction tells us that there will be an induced EMF in the coil. So now, suppose if we move the magnet closer to the loop, the flux increases and there will be induced EMF. And Lenz's law tells us that the flow of the current will be such that it will produce a magnetic field which opposes the external magnetic field coming from the magnet. So the coil in this case will produce a magnetic field which has magnetic field lines as shown. And if the magnet were to be moved away from the loop, then the induced EMF will be such that the flow of current will be reversed. So this is the idea of the Lenz's law, and this has practical applications in everyday life. I will explain, for example, how magnetic levitation works for trains. So here we have these figure 8 shaped coils placed along the track on both sides of the train, and these coils are not powered externally, so it's just a closed loop of conductor which is like twisted in the shape of an 8 and placed on either sides. So in this train you have superconducting magnets on either sides, and the currents in the superconductors are arranged such that the opposite polarity of the magnetic field is facing each other. So effectively these two independent magnets, they combine to create this combined magnetic field. And so this resembles a magnetic field created by a bar magnet, for example. So you can imagine a bar magnet moving instead of a train on this track, and the field lines, they are passing through this figure 8 shaped coil. So there is some flux associated with it. So how does levitation work? Let's understand it. Here we have a bar magnet which is symmetrically placed with respect to this coil. So as the bar magnet moves along the rail, uh, which is symmetric with respect to the coil, so the flux is the same. So the top and the bottom part of the coil. So what is the change in what is the direction of the EMF that is induced by the change in the flux as the magnet moves along the rail? Well, you realize that since the coil is twisted, there is no net induced EMF in the coil. So the net flow of current in the coil is zero. If the bar magnet is not symmetrical with respect to the coil, so here for example, if the magnet has gone down, then the flux through the bottom part of the coil is larger compared to the upper part of the coil. So let's see what happens in this case. So now in this case, the imbalance of the flux through the upper and bottom part of the loop causes a net flow of current in the coil. So now we have this Lenz's law coming into action. So the bottom part of the coil now produces a magnetic field which opposes the magnetic field of this bar magnet, and since the coil is twisted, the upper part will have a magnetic field which is trying to attract this bar magnet on the towards itself. So now here this red arrow shows the force of repulsion from this bottom part, and green arrow shows the force of attraction from the top part. And the same thing happens on the opposite side here, which is not shown. So effectively what happens is that the horizontal components of this magnetic forces cancel and the vertical components add. So basically you now have a net force in the upward direction, which is shown by this green arrow. Okay, and this gravitational force, which is shown by this orange arrow, is pointing downwards. So now when the magnetic force exceeds the gravitational force, this bar magnet will rise. So that's the principle behind this magnetic levitation. And when the bar magnet, for example, reaches a location which is symmetric with respect to these two coils, then again the flux will become the same through the two coils, and then there will be no net force as we have seen earlier. So this is how levitation works, and this is implemented in Japan, for example. They were able to demonstrate a levitation of about 3.9 inches. So let us see how we can demonstrate this Lenz's law in our laboratory. Our demonstration of the Lenz's law involves a very simple setup. We just have a copper pipe and some magnets which we will drop through the pipe. So on the right hand side, I'm showing you the cross section of this experimental setup. So when these magnets are falling through this pipe, the flux is continuously changing through different cross sections of the pipe. So for example, at some instant when the magnet is at this location, so the field lines are shown by these green arrows, the bottom part of the tube experiences an increase in the flux because the magnet is now moving closer and it's moving down. So this flux causes an induced EMF, and the flow of current is such that it produces a magnetic field, and therefore it tries to repel the magnet up. However, on the top part, the flux is decreasing because the magnet is falling, and therefore this causes a flow of current in the reverse direction, and it tries to attract the magnet in the upward direction. So effectively, there is a the magnet experiences a if you can say like a magnetic friction as it goes down. So effectively, it just slows down, it falls. So that's what we are going to demonstrate. Our experimental setup is shown on the left hand side. So we have a copper pipe of about 1 meter length mounted on a stand, and we just drop a magnet from rest in this pipe, but we also drop a coin just to show you how fast an object would fall through height of about 1 meter. So for the coin it's free fall, but for the magnet, because of this magnetic induction Lenz law, the motion will be about much more slow. So you just see that. So this coin is just being dropped. So that's the free fall of the coin. And then my colleague will just show you the magnet and then release it into the pipe. Okay, see, you can see that it takes considerably longer. It's very interesting to look at this effect from the top. So on the right hand side, we repeat the experiment again with the coin and the magnet. So just look at it. It's a free fall for the coin. Not the same for the magnet. It takes a bit longer. So this is Lenz's law in action. I'm grateful to all of you for your kind attention. Thank you so much. Have a good day. Bye bye.